Hi everyone, today we'll talk about the injection molding 1. Injection molding is very versatile technology that you could use to make a variety of different products. For example, this all sorts of caps are made from injection molding process. Now, in general, injection molding is the most important process used to manufacture plastic product, and in fact, more than a third of all the thermoplastic are injection molded. More than half of all polymer process equipment it is for injection molding. And the injection molding process is ideally suited to make mass-produced parts of a complex shape and that also require precise dimensions. In fact, in this region, where we have a lot of injection molding components, such as Philips, Inton, the SMC, Naloto, contour, lots of plastic components that deal with injection molding. It's very important for all of you to learn a little bit about the injection molding process. Alright, now let's look at injection molding machines. You will have three main components or units. The first one is the plasticating unit right here. The second is the clamping unit. And in the clamping unit, the very important component is the mold, and we'll talk about later. Alright, first let's look at the plasticating unit. And this is a hopper, right? As we learned in extrusion. This is a hopper where you put in a material and that's connected with a motor. This is a screw inside. This is a screw. And this is the nozzle. That's the nozzle. And another very important, this is the check valve. The check valve is a very important part for injection molding. We prevent material backflow, but also allow material to flow front. So I have a screw, injection molding screw, and you can see this valve. This valve is called a check valve, okay? This is the check valve, and that's the nozzle, okay? So your material can flow through the check valve to the nozzle, but as well as prevent the material to flow backward. That's the function of this check valve. All right. If you have injection molding machines and we have give you the label, this is how you read it. The T stands for the maximum clamping force in metric tons. The P is related to the Vmax, which is the maximum short size your machine can produce. Pmax is the maximum injection pressure. If you know a little bit about thermodynamics, Vmax times Pmax tell you basically how much work your machine can perform. Generally, the higher the clamping force, more expensive your equipment is going to be. Alright, this is a mold. And the mold is a very complicated component itself. It has many functions. For example, it will be able to distribute plastics between the barrel and the part. It also will provide an escape for the air or gases present, so it's a venting purpose. It can also create the part shape depending on the cavity and core, and also it could be able to cool the plastic. So generally, you will have a coolant cooling line go through the mold. It also provides a method to remove the part from the mold, and that's ejection. And you can see there's many such functions for injection molding and mold. And in fact, the mold design and the manufacturing business is also very huge in injection molding field. Again, it will be able to distribute materials, vent, create a shape, cool the plastic, and also be able to eject the parts after the part has been made. Here, this slide can talk about the mold core and the mold cavity. And the next, we're going to talk about the spool bushing, locating ring, support plate, ejector bar, ejector pins, ejector box, And also there are spools, runners, gate, and cooling channels. They are very important parts of the mold. In fact, I have a quiz designed on detail, so please read through the few slides and finish that quiz. Here, I do want to point out, generally people talking about runners, okay? What's runners? Runners is the channel that carry the molten plastic from the spool to all of the cavities that must be filled. So if I give you examples, do you see this? Okay, I hope you see this, okay? So this is where your material can come from, and this is the runners, okay? And this little entrance, that's the and that's the gate. So here is the runners, okay? And that's the part you're going to be make. So we could have a so-called cold runners. The cold runners, it is the material solidify inside this runners and is attached to the part and must be separated after the part has been ejected from the part. There's another type of runners called hot runners. The hot runners can independently heat the channels, allowing the contained material to be melted and detached from the part. So the big difference is, for cold runners, your material inside runner will come out with your part and you need to perform a secondary process to separate them. For hot runners, you don't, because the material inside the runners will stay melted and they won't come out with the part. And generally, hot runners require a higher setup cost in the beginning, but in the long run, it should save more material for you. Okay, this is the quiz I referring to. What I need you is to label different parts of the mold. Alright, now let's talk about the injection molding cycle. There are 7 steps of injection molding cycle. Okay, the first one, do you see this? The first one is mold closing. We can go over the next slide and look at it. So the first step is mold closing, where you want to close your mold as safely as possible and fast as you can. The second is an injection unit move forward. Again, you want to perform this as fast and safe as you can. Then you will start the injection step or mold filling step. This is set by a certain velocity, and generally in this step you only fill to 95 to 98% of the fullness of the part. You do not completely fill the part. Okay, you only fill 95 to 98% fullness. Then you can hold your pressure. You just want to maintain enough pressure to fill the last 2 to 5% full of the part, and just long enough to allow the gate to freeze. Then your injection unit gonna move back. Then you're gonna start the plasticating or screw recovery step. Screw is rotating and moving back to the meter to meet the next shot. Again, it's set as fast as possible without introducing too much shear. Number 7, you mold close and then you eject your part out. Parts removed efficiently without hanging up in your mold or introduce stress marks. These are the 7 steps for injection molding process. Again, I'm going to repeat briefly one more time. The first, you close your mold, then your injection unit move forward. You start the injection, but you only eject to 95 to 98% fullness. Then you hold your pressure and fill the last 2 to 5% of your part. Afterwards, your injection unit goes back and you start the plasticating unit to prepare for the next shot. The last step is, once your part is cooled, your mold open and the parts being injected. There are several very important parameters that have a great effect on the process outcome. The first one is melt temperature. Okay, for amorphous temperature, amorphous materials, generally you should set your melting at least 100K above Tg. Again, remember what Tg is? Tg is the temperature where material transit between glass in the rubber state. Where does the heat come from? Well, you have heat bands that only contribute about a quarter of the total heat needed. The majority of the heat comes from shear heating. So this is about melt temperature, and the first step you want to set up the melt temperature is according to this data sheet you find at IDs. Generally, they will tell you what temperature you should set your injection molding at. The second important parameter is mold temperature, and that's related to the VICAS softening temperatures. And I will tell you in the next slide what VICAS softening temperature is. Generally, you set your mold temperature slightly below the VICAS softening temperatures. Again, this is affected by coolant temperature, how they flow, whether they have tubular flow, laminar flows, and again, you can put a thermocouple in the mold, and that would give you the real temperatures of your mold. The third important parameter is pack hold pressure. Remember, after you inject to 95 to 98% fullness, then you start the holding pressure step. In this step, you just want to have just enough pressures to fill the last 2 to 5%. And also, your processing is related to fill speed and time. Fastest time is desirable, shorter time is desirable, but again, sometimes it's not well controlled. Again, we will talk about, for example, how do you know what pressure you set at, how do you know what speed you should set your injection molding at next time. Okay, now let's look at the VICAS softening temperature. Alright, so VICAS softening temperature, this is the apparatus set it up to measure the VICAS softening. Do you see this sample in red? And that's a flat needle, okay? And this is enclosed in an oven where you can vary the temperature. So VICAS softening temperature, it is the temperature at which the specimen is penetrated to a depth of 1 millimeter by a flat-ended noodle with a 1 square millimeter circular or square cross-section. You could use 10 or 15 newtons. Okay, so VICAS softening temperature is the temperature where your specimen will be penetrated to depths of 1 millimeter. Think about it. If you set your mold temperature higher than VICAS softening temperature, what would happen? Well, if you set your mold temperature higher than VICAS softening temperature, when your ejector pin try to push your parts out, it might leave a dent, right? It might leave a dent on your part, and that would give you a defect. Alright, that's what I have for today, and I hope to see you all of you next time for injection molding 2.